welcome. In this session in linear data analysis, we'll explore how our simple model of an artificial neuron is making a hyperplane decision. Let's begin by recalling a hyperplane. And the way that we've usually drawn this is we have a hyperplane and we're referring to it as double-barreled H, and it has a weight vector, which is not necessarily a unit vector, that's associated with it. And if a vector is on this positive W side of the hyperplane, we'll say that that's in set 1, and then if it's on the opposite side, we'll say that that's in set 2. And the question is, for a given vector, so if we're given an observation that we're gathering into a pseudo vector x1, what we want to know is which side of that hyperplane is it on. Well, to do that, what we do is the hyperplane is given by a weight vector and a bias scalar. And what we want is the pseudo distance. And this is not an exact distance, because the exact distance would require that W has a unit length. But the pseudo distance will say that the pseudo distance number I is going to be, and we could say defined as or just equals, what we'll do is we'll transpose the ith observation, multiply it by the weight vector, and add the bias scalar. And now what we have is our hyperplane decision is if ui is greater than or equal to 0, we will assign xi to set 1. Now, what we'll want to do is, in a binary classification problem, we'll be given a lot of data. And what we want to do is we want to learn this hyperplane. So we want to learn W and B. And it will be computationally easier if we augment. And by augment, what we'll mean is, let's put a hat over it. What we'll do is we'll take this weight vector and we'll augment it with the bias scalar. And to correspond to that, what we'll do is we'll say that our ith observation is we take the ith vector-like object that's x and we'll augment it with a 1. And now what we can do is we can see that ui, if we say that that is x hat I transpose times w hat, well, that is the same as saying if I transpose xi hat, that's the same as transposing xi and augmenting it with a 1 on the right side, and then w will look like the w vector augmented with the bias scalar. And now when we compute that, this is xi transpose w, xi transpose times the w vector, plus 1 times the bias scalar. And so we can compute this. And the reason that we do this is not just computational efficiency. What it means is that in our code, we won't have to be carrying this bias scalar around, and as we propagate it in future courses, if you have to propagate this through neural nets, it will be really useful if instead of having the bias scalar off on the side, we incorporate it into an augmented vector. So now, the final part of of an artificial neuron is its activation. And the general activation is a function phi, and we can write phi as taking a real number and mapping to another real number. And in our case, this will be a very, very simple function. So we could write it that way, or we could also say that what it's doing is it's giving us a score. So we can say that it gives us that the activation function is giving us a score, and in particular, the score that we're interested in is the score of the linear sum. So this is how we do it in general. So now, let's ask, how do we, I'll say, match the neuron output to a label? And let's recall that a label, y sub I, was either 0 or 1, and that's the convention that we have in artificial neural networks. Well, what we can do is we can quantize. And quantize, so we'll quantize either, we'll write that as a quantization function that takes a real number and then maps it into this set of 0, 1. And it's either we'll take the linear response for data vector I, or we'll take the linear response of the score. And we can do either. What we'll do is we'll just, in our simple model, we'll just quantize the score. And the way that we usually quantize the score is to use the Heaviside step function. And this is usually called either the Heaviside function or the step function, and will be momentarily redundant just so that we can really remember this. So what that looks like is the Heaviside step function, which we'll write as Heaviside, and I'll just say we're taking the variable u. It could be the variable z. But we will define this as its output is 1 if u is greater than or equal to 0, and it's 0 if u is less than 0. And so that is the quantization function that we'll use. What that will do is this. Let's imagine that this is our u-axis. So this is the output of a pseudo-distance that our artificial neuron is computing. And we have the Heaviside result here. So let's suppose that that we have a vector that's on the negative side of the hyperplane. Well, if we do the linear computation of the pseudo-distance over here, what we'll get is a negative number. And the Heaviside function says if it's a negative number, then we'll respond with 0. And that would correspond to us classifying that data vector as being in set 2. Now, imagine that the data vector that we have is on the positive side. When we calculate that pseudo-distance, what we'll find is that it's a positive number. And the Heaviside function for a positive number will jump up, and it will now classify every vector that's on the positive side of the hyperplane by outputting a 1. And so what we'll get is this. We have a quantization function, which is the Heaviside step function. It's simply saying it's 1 if this is a non-negative number, and it's 0 if it's a negative number. And that will cause the pseudo-distance to be transformed into a classification of 0 or 1. Let's summarize binary classification in the context of our simple model of an artificial neuron. What we have is we have data coming in, and each one of these data has a label that's either 0 or 1. And the assumption is that we have this label for every augmented data vector that we have. This label is going to be such that the data are classified as being in set 1, provided that that label is 1, and otherwise they're not in set 1, and we'll just say they're in some other set 2. So the ideal match that we want is when the label is 0, we want our linear weighted sum, or our pseudo-distance, to be negative, and when that label is 1, we want our pseudo distance to be 0 or greater than 0. So if we get these matches, then we have complete accuracy. That, of course, doesn't usually happen with real empirical data, but this is certainly the ideal that we want to aim for. What have we learned in this lecture? Well, we're now able to augment the data vector for neural computation. We can use this augmented data vector to compute a pseudo-distance, and we can quantize the pseudo-distance, which is the same as activating our artificial neuron.